CSE 571, Probability Basics. Hi, today we are going to go through some definitions and basics of probability which you will use throughout this course. In everyday life, we all hear about words such as luck, uncertainty, doubt, fortune, and chance. What do they all have in common? Well, to some extent, they all try to measure the uncertainty. We all have heard this famous quote of Albert Einstein that God does not play dice with the universe. So relying on intuitions in riskful situations results in inaccurate predictions or overconfident decisions. So why do we study probability? Well, since mathematics is the logic of certainty, we can say probability is the logic of uncertainty. Let's take a look at probability applications in different fields. In biology, gene inheritance and mutations are intertwined with probability. In medicine, success rate of clinical procedure or medical treatment is heavily reliant on probability. In computer science, machine learning and artificial intelligence and all of its applications are relying on probabilities and calculating the uncertainty. In physics, understanding of quantum physics relies on probability. In finance, calculating the risk of investments and success rate of determination of. In biology, gene inheritance and mutation pretty much relies on probability. In medicine, measure the success of a clinical procedure heavily relies on probability. In computer science and machine learning, I have to start over. Okay. And what? Put this here. Let's take a look at probability applications. In biology, gene inheritance and mutations are hugely relies on probabilities. In medicine, the success rate of a medical treatment heavily relies on probability. Computer science, machine learning and artificial intelligence pretty much are calculating the probability of uncertainty. In physics, quantum physics relies heavily on understanding the probability basics. In finance, risk determination and success rate of investments are based on probability. Let's take a look at some definitions. A sample space S is set of all possible outcomes of an experiment. So for instance, if I have an experiment such as tossing a coin, I will have head and tail as my space. So an event which can be the probability of heads coming would be a subset of a sample space. Let's take a look at some definitions. A sample space. Let's take a look at some definitions. A sample space S is the set of all possible outcomes of an experiment. For example, if we toss a coin, our sample space is head and tail. An event is a subset of a sample space. For instance, the event of head is a subset of the space A. Let's take a look at some definitions. A sample space S is the set of all possible outcomes of an experiment. For instance, if we toss a coin, the sample space will be head and tail, assuming that the coin has only two sides. So an event, which in this example would be heads, is a subset of a sample space. Assuming that all outcomes are equally likely and the state space is finite, the probability of the event, in this case, the probability of head happening, is the number of favorable outcomes over the number of possible outcomes, which is 1/2 or 0.5. Simply, the probability of an event not happening is 1 minus the probability of an event happening. This means that sum of all the probabilities should be 1. If an event is a subset of another event, the probability of that event should be lower than the probability of the main event. Similarly, if we want to calculate the probability of two events together, we have to sum the probability of those two events and we have to subtract the intersection of those two probabilities. We call two events independent if and only if the probability of the intersection of those two events is the multiplication between probability of A and probability of B. For simplicity, we write the probability of the intersection of A and B with a comma. If we want to calculate the probability that at least one of the events occur in a state space, we have to calculate the probability of the union of all those events. Similarly, if we want to calculate the probability that none of those events happen, we have to subtract those events from 1. If we want to calculate the probability that all of the events happening, we have to calculate the intersection of those events. Note that here, by that all of the events occur, we mean that all of those events occur at the same time, which is equivalent to 1 minus the probability of none of those events happen, or at least none of those events happen. Let's take a look at an example. Suppose we toss two coins. Assuming that each coin has two possible outcomes, what is the probability that we see two heads? So first, let's calculate the probability of the state space. Let's calculate the state space. We have heads and tail, and we have heads and head, and we have tails and head, and we have tails and tails. So what is the probability that we see two heads? Well, our favorable outcome is 1 over 4, or 25%. What is the probability that we see at least one tail? Here, we are calculating the probability of heads and tail union with tails and head union with tails and tails, which is 3 over 4. What if we have two dice and we roll them at the same time? Assuming those dices are fair, what is the probability that we don't see any 6s? To calculate this probability, it is easier to calculate the probability of seeing at least 1 6, and then we subtract it from 1. So what is the probability of we see 1 6? It's 1 over 6 for one dice. And since we have two dices, it's 1 over 6 for the second dice, and we subtract it from 1. So what we have is 35 over 36. Let's take a look at another example. Assume that we have a fair coin. Therefore, the probability of a head is 0.5. How many heads would you get if you toss a coin for 4 times? What about 20 times? And what about 100 times? Before we answer this question, let's take a look at this example. If x is a random variable with arity k, we want to define x as a random variable with arity of k if it can get exactly one value out of x1 to xk. Arity is the number of possible inputs that a value can get in this situation. So for instance, if we assume that our event is x, we can get from 0 up to 4 times heads. When we toss it 20 times, we will get 0 up to 20 times. And if we had 100 times, we'll get 0 up to 20, up to 100 times. Let's take a look at another example. We toss a fair coin 2 times. So what is the probability? Let's take a look at the probabilities. To understand the random variable better, let's take a look at another example. We toss a fair coin 2 times. Since the probability of the coins are independent from each other, to understand random variable better, let's take a look at another example. We toss a fair coin 2 times. Let's see what are the probabilities that we see any of these events of the state space. To understand the random variable better, we're going to take a look at another example. To understand the random variable better, we're going to take a look at another example. We toss a fair coin 2 times. Let's see what is the probability of any of the state space event happening. To understand the random variable better, let's take a look at another example. We toss a fair coin twice. The probability of we see 0 heads is 1/4. Why is that? Because the probability the first coin gets head is 1/2, and since the probability of the second coin becomes head is independent from the first coin, we get 1/4. What is the probability of we see 1 head? Well, it is the probability of we see heads and tails plus the probability of we see tail and head, which is 1/2. What is the probability that we see 2 heads? That probability is 1/4, the same as the 0 heads. To understand the random variable better, let's take a look at another example. We toss a fair coin 2 times. What is the probability that we see 0 heads? So the probability that we see 0 heads would be 1/2 for the first coin, for the first time the coin becomes tails, and 1/2 for the second time that the coin falls on tails. So it's 1/4. What is the probability that we see 1 head? Well, that's the probability of we see heads and tails plus the probability of we see tail and head, which is 1/2. What is the probability that we see 2 heads? Well, it is 1/2 for the first coin to fall on heads, and it is 1/2 for the second time that the coin falls on heads. So it is 1/4. So it is most probable that we get 1 head over 2 heads or 0 heads. If you look at the probability of 1 head and compare it separately with 0 head and 2 head, it is obvious that we will see 1 head most probably. But if you look at probability of 0 head and 2 head together, the uncertainty is considerable. In this case, the uncertainty is 50% comparing to see 1 head. So the probability that we see one head is 50%, and the probability that we don't see one head is also 50%. To calculate the uncertainty, we define probability mass function. To understand the concept of random variable better, let's take a look at another example. We toss a fair coin 2 times. What is the probability that we see 0 heads? So the probability that we see 0 heads is 1/2 for the first time that we toss the coin to fall on tail, times 1/2 for the second time that we toss the coin to fall on tails. So it is 1/4. What is the probability that we see one head? Well, it is the probability that we see head and tail plus the probability that we see tail and head, which is 1/2. What is the probability that we see 2 heads? It is 1/2 for the first time to fall on heads, and it is 1/2 for the second time to fall on head again, so it is 1/4. So if you look at the probability of one head and compare it with 0 heads and 2 heads, you'll see that the probability that we see one head when we toss a fair coin 2 times is more than we get 0 heads and 2 heads. But if you look at the probability of 0 heads and 2 heads together, the probability of not seeing one head is 50%. So in this case, the uncertainty is considerable, which is 50%. To calculate the uncertainty better, we define probability mass function. Probability mass function is a function that calculates the probability of event X becoming a specific value xi. Needless to say, the sum of all the probabilities for different events in the state space has to be 1. The union of probability of different events, while I and j are different, should be the summation between those 2 probabilities. An intersection of 2 different events happening should be 0. The union of all events happening at the same time is the same as we calculate the probability of xi x1 plus p x2 all the way to p xk, which in this case is to calculate sigma of all px equals xi, which we know from above equals to 1. How can we provide a mathematical function that provides the probabilities of occurrence of different possible outcomes in an experiment? Now that we see random variables in one example, how can we provide a mathematical function that provides the probabilities of occurrence of different possible outcomes in an experiment? Well, let's take a look at different distributions. Now that we learned more about random variables, let's see how can we use the function, the probability mass function in different How can we provide a mathematical function that provides the probabilities of occurrence of different how can we use let's think about how can we use the mathematical function. Now let's think about how we can use probability mass function to provide the probability of occurrence of different events, of different possible outcomes in an experiment. Now let's think about how we can provide a mathematical function that can give us Now let's think about how can we provide a mathematical function that we can use that function to calculate the probability of different possible outcomes in an experiment. Well, to answer that question, let's look at common distributions. The first one is uniform distribution. Uniform. If you have an experiment of different balls in a box, if you have different balls in a box and each one is from one color, and we want to calculate the probability of we pick up one color from, suppose you have balls. Now let's think about how we can provide a mathematical function that we can use to calculate the probability of different outcomes throughout an experiment. To answer this question, we have to think about how different events will be distributed in the sample space. Let's take a look at different distributions. First one is uniform distribution. Suppose you have balls with different colors in a box, each from one color, and you want to calculate the probability of the ball that you pick being from one color. So that probability is 1 over the number of balls you have. In this case, is 1 over 5. The second distribution is binomial distribution. We saw an example of coin flip. To calculate the probability of a coin flip, to calculate the probability, we have to use this function. You can apply this function to the previous example that we had to see how it works. And the third distribution is joint distribution. If we have two random variables, x and y, that they are independent from each other, their joint distribution together is the intersection of between those two events happening, and the summation of those two events is supposed to be 1. For example, let's think about you and your friend toss two coins together, you for 50 times and your friend for 100 times. And you want to calculate the probability of you getting 21 heads and your friend gets 70 heads. To calculate that probability, we have to calculate the probability of sigma from (0 to 50), and for your friend from 0 to 100, the probability of you get heads for 21 times and your friend get heads for 70 times. This probability should be sum up to 1. Got this probability. Now let's think about conditional probability. A conditional probability is the probability of an event happening given the occurrence of another event. That means that the happening of the first event is somehow related to the second event. For instance, the probability of you get an A in artificial intelligence given that you have studied the material for the exam is dependent on each other. To calculate that probability, you have to calculate the intersection between those two events happening over the second event happens. And as we mentioned, for simplicity, you can mention the first part, the top part as x equal x and comma y equal y. Now if x and y are two discrete random variables, the probability of xi, x is specific event, marginalization if we have two events x and y as two random variables. Marginalization is the probability of a subset of collection of random variables, which is the probability distribution of variables contained in the subset. Let's think about marginalization. If x and y are two discrete random variables, to calculate the probability of x becoming a specific event, which is a marginal probability, we have to calculate the probability